Okay, so today we are very pleased to have Nikolas Breuckmann, who is going to speak about LDPC quantum codes, recent developments, challenges, and opportunities.
Yeah, thanks very much, Carl, for the nice introduction and for having me. So this is a talk that I've given in a slightly different form in the past, but since this is like a math and computer science seminar, I added like the more gory mathematical details that I kind of try to hide when I kind of usually talk to a broader audience. I hope I did a good enough job. I want to first of all kind of give it a disclaimer that whenever you don't understand something or you want to kind of dig more into the details, then don't hesitate to interrupt me and ask questions. And so actually, I very much invite you to do so. Okay, so let me get started, and let's start very easy. I assume that many of you have heard about quantum error correction. The very overarching main idea is that we have some number of qubits k that we want to protect against errors that are inevitable in our physical devices. And we protect them by encoding them into non-local degrees of freedom of a much larger set of n so-called physical qubits. So these are the qubits that we have in the lab. Again, the overarching idea is that once errors occur, then we continuously keep measuring so-called check operators, which give us information about what errors occurred. And then we use this information, can process it with a classical algorithm and apply a recovery operation. Okay, so first of all, let me clarify one thing. So when I talk about a quantum code, I usually mean an infinite family of quantum codes. And the talk is titled LDPC quantum codes. So that's a subclass of all quantum codes, which fulfill two conditions. So first of all, each check operates on a constant number of qubits, and each qubit participates in a constant number of checks. And you can see I now put like parentheses about quantum in the Q. So the same definition holds for a class of classical codes, which is widely used in pretty much everywhere around you right now. So in Wi-Fi technology and also 5G and so on. And this has been very successful. So it would be nice if we could kind of use these LDPC codes in the quantum realm as well. Okay, the quintessential example of an LDPC code and also like a quantum code itself is the so-called toric code. So this is defined from a square tessellation of a torus, where we identify the edges with qubits, and we have two types of check operators. So first of all, we have a check operator which acts as Pauli X on four qubits. Yeah, so for each vertex, we have an XXX Pauli operator, and for every phase, we have a ZZZ Pauli operator acting on all qubits incident to a phase. Okay, one important concept in quantum error correction are so-called logical operators, which are the operators which act on the encoded qubits. And if an error happens such that it supports a logical operator, then this leads to a loss of the encoded information. So quantum codes come with two parameters, and these parameters will be quite good for these LDPC codes. So first of all, there's the encoding rate, meaning how many encoded qubits we have per physical qubit. Yeah, so how efficient our code is. And then there's the distance d, which tells us how many single qubit errors the code protects against. And this is the same thing as the minimum weight of a logical operator. And so there's already there's some no-go theorems kind of restricting these parameters. So there's a Bravi-Poulenc-Terhal bound, which tells us that if we have planar codes, something which is can be kind of laid out in 2D Euclidean space, then any code will kind of be bound to having k times d squared being bounded by the number of physical qubits. Yeah, and we will see how LDPC codes can generally have more favorable encoding rate and distance. So when you talk to people, usually they mean something more specific when they talk about LDPC quantum codes. So let me just give you this little disclaimer before we dive into more details. So let's say we have the set of all quantum codes, then like some number of them are LDPC. And this includes like very famous codes that you might have heard of, the surface code, the toric code, and color codes. However, usually people mean codes which have a very high distance and a very high rate. Yeah, so this is usually what people refer to when they talk about LDPC codes. They don't mean the more common surface toric code and so on. Okay, one more thing is the so-called CSS construction. So I won't actually discuss arbitrary quantum codes, but so-called CSS quantum codes. And they define as follows. So first of all, I talked about classical codes before. So classical linear binary codes, I can define by giving you a matrix, yeah, a binary matrix with entries in F2. And I define the code as the kernel of this matrix, yeah. So it's just a subspace of F2 to the n. And similarly, CSS codes, I can define by giving you two check matrices, HX and HZ, which are, again, both binary matrices. However, they have to fulfill a condition, and this condition is that HX times HZ transposed has to be equal to 0. Yeah, and I won't go into too many details. So this condition essentially kind of comes from the condition that the checks have to give us observables. Yeah, so we have to be able to measure them, and in order to be compatible, these observables have to commute. And this commutativity condition is essentially encoded in this equation. So this is where it comes from. And yeah, restricting ourselves to these CSS quantum codes is not a large restriction. So it was shown by Bravi, Lemos, and Terhal that another large class, so-called stabilizer codes, can be mapped onto a CSS code with only minor loss in parameters. Yeah, so this is why we can generally, if we just kind of care about the scaling of parameters inside a family, we can kind of relax and only consider CSS codes. Okay, so there are mainly two ways of getting CSS codes, and yeah, first of all, there are geometric constructions, and then there are so-called product constructions. And I will start with the geometric constructions first. And the idea behind geometric constructions is using simplicial homology. And this allows us to take topological spaces and turn them into LDPC quantum codes. So yeah, let me introduce the main notions of simplicial homology. So first of all, when we take our topological space, we assume that it's triangulable, and meaning that we can subdivide it into vertices, edges, faces, and so on. And yeah, these cells they span under formal linear combinations binary vector spaces, so F2 vector spaces, and these are denoted Ci. And yeah, there's a mapping between chains of adjacent dimensions. So I can take an I chain and map it onto an I-1 chain. And I will kind of explain how this boundary maps work in a minute. But let me just say I write this as a map. But actually, since we have a distinguished basis, I will always consider them to be matrices. So I hope I don't offend too many mathematicians who might be in the audience if I kind of swap between these two things back and forth. Yeah, so these are just incidence matrices between the cells. So if I have, let's say, an edge, then applying the boundary operator will just give me the endpoints of this edge, so the two vertices which belong to this edge. And the all-important property in homology generally is that if we apply a boundary operator twice, then this gives us 0. Yeah, so the catchphrase is that boundaries do not have boundaries themselves. So if you just take, like, say, a sphere, a ball, then the boundary of this will be a sphere, which itself is boundaryless. Okay, so what does this have to do with coding theory? First of all, if we only have a single boundary operator, yeah, this condition is kind of trivially fulfilled, and I can define classical codes as length 1 chain complexes. Yeah, so a chain complex is just this diagram where I take the I chains and I just draw the arrows of the boundary operators or the boundary maps kind of going between them. And so only taking like a length 1 chain complex defines or gives me a classical code, where the boundary operator is just the parity-check matrix that we've seen a minute ago. And a quantum code is nothing but a length 2 chain complex, So this means, since this is kind of fulfilled, we can define 2 parity-check matrices, and we obtain a valid CSS code in this way. And I will go through an example right now. So let's consider again the toric code. So first of all, let's look at what happens with these chains. So let's take a 2 chain, which is just a single phase. I can apply the boundary operator, and I obtain the linear combination of all the edges adjacent to this phase, and I apply the boundary operator again. And since there are 2 edges adjacent to each vertex, this is just giving me 0. So now, in order to define the code, I can identify all qubits with edges. So the 1 cells are identified with my physical qubits, and I define the code by setting the parity-check matrices to be the boundary operators. And then, due to this homology condition, I immediately obtain that this is a valid code. So it fulfills this condition, which ensures the commutativity of the observables. Okay, but this immediately generalizes to much more complicated geometries. So there's nothing special about the torus. So I can take any surface and not only triangulated but kind of tessellated in using a tessellation or cellulation. And this also works in high dimensions immediately. So I can immediately take arbitrary triangulable manifolds, and I can assign a quantum code to them. And the reason why we want to do this is because we can leverage results from geometry to quantum coding theory. And I want to again stress that we use these spaces for constructions, not for physical layout. So when I talk about, I don't know, 4-dimensional hyperbolic manifolds, then this doesn't mean that we need a 4-dimensional hyperbolic space to kind of realize these codes. In the end, what we obtain is just some set of observables that we want to measure, and these can, in principle, be non-local in certain architectures. But I will kind of talk about this later as well. I should also mention that actually the record distance scaling for quantum codes for almost 20 years was held by a construction due to Friedman, Meyer, and Luo. I won't go into this construction, but if somebody is interested, then I can certainly talk about it, how this works. Okay. So let me now go into more details of like how the code parameters relate to the geometric quantities. So first of all, we know that the physical qubits in the construction are these I-dimensional cells. So that means if we subdivide our manifold uniformly, so using like finite volume cells, then we get a uniform density of the I cells, which are the physical qubits. And this immediately tells us that the number of physical qubits n scales with the total volume of the manifold that we construct our code from. So this is like the first relation. Okay, so what about the encoding rate? And this is again where homology comes into play. So homology tells us about our encoding rate. As for the experts, I will only talk about logical Z operators now, and they correspond to what's called essential cycles. And an essential cycle is something that is in the kernel of a boundary operator, but it's not in the image of the previous boundary operator. So all things which are kind of closed submanifolds, but which are not boundaries of any subvolume. And the space of these essential cycles are the so-called homology groups. So just the quotient space of the kernel modulo the image of the preceding one. And thereby the number of encoded qubits is exactly the dimension of these spaces. Yeah. So k scales with the dimension of the ith homology group. So for example, we could have taken the surface here, and we know that there are 2 times the genus number of essential cycles in a 2D surface. Yeah, so these would give us our logical operators. Okay, there's a deeper, so this was only topology, but there's like actually a relation to geometry. And yeah, so this relation comes from the so-called Chern-Gauss-Bony theorem, which is one of these theorems which relate geometry to topology. And it tells us that the Euler characteristic, so the alternating sum over the homology, the dimensions of the homology groups, is the same thing as this integral over the Pfaffian of the curvature form. And in particular, this simplifies if we consider, let's say, constant negative curvature. Yeah, so this will just be, the integral will just be proportional to the total volume of the manifold. And let's say we consider 2 dimensions or 4 dimensions, then we can actually solve for the respective homology groups, so the first or the second homology group. And we obtain a lower bound, well, here in this case, an equality, in terms of the area of the manifold, which we already seen is given by which gives us the number of physical qubits that we have. Yeah. So in both cases, we obtain a lower bound of k by n, which is linear. Yeah. So this kind of suggests that if we take hyperbolic manifolds, we can obtain so-called finite rate codes. Yeah. So where essentially, if we invest some number of physical qubits, we obtain a proportional amount of encoded qubits. And this is very different from, let's say, the Euclidean case, let's say the toric code, where regardless of how big we make the torus, it will only have 2 essential cycles. So we don't actually gain anything from in terms of encoding rate by increasing the size. Okay, the last parameter is the distance. So again, like how well our encoded information is protected. And this is something to do with a field called Systolic Geometry. And again, the idea is that we look at these logical operators, and the distance is just given by the minimum weight of logical operators. But this is the same thing as asking for the minimum volume of an essential cycle. Yeah, so yeah, the distance is just is kind of related to these minimum volumes of these essential cycles. And this is something that has been studied. I don't want to say so. This has been studied in the math literature, and this is called systolic geometry. And yeah, so people produce in general inequalities or bounds on the scaling of these volumes. And like classical results are, for example, Gromos inequality, which is a general upper bound if I is equal to 1. Yeah, so for one-dimensional essential cycles. But also lower bounds, which is what we are interested in. Like we want to lower bound the distance. We want to know how good our code is in the end. And this is an example of this is Anderson's inequality, which lower bounds these volumes for hyperbolic manifolds. And again, so I won't have too much time into going. So this is like a vast area, and not everything is pertains. It's in this area, kind of is important for our purposes. But yeah, there's a nice review article by Larry Guth about this. I should also mention that the information flow now seems to be also go in the opposite direction. So Friedman and Hastings showed that we can essentially take quantum code and turn it back into a differentiable manifold. And by doing so, we can answer questions in systolic geometry via quantum coding theory, which is kind of interesting. Okay. Yeah, so let me just kind of, leave you with 2 examples of geometric LDPC codes. So one are hyperbolic surface codes, so 2-dimensional examples. So I've already argued that the encoding rate is linear, which is optimal, and it's also very similar to other codes which have been more studied in the literature. However, the distance scaling is not very favorable; it's only logarithmic. But this can be fixed if we go and consider higher dimensional hyperbolic codes. So they have better distance scaling, which is n to the epsilon for some epsilon. I should mention that actually the optimum epsilon is unknown. So I mean, we don't really know like how large the distance can be. There is an upper bound for a subclass of hyperbolic four-dimensional manifolds, so-called arithmetic manifolds. But I don't think there's a general known upper bound. Yeah, and they also have like some other nice properties. So they can be the error correction procedure is much more simplified and also more robust once we take measurement errors into account. Okay, and just maybe kind of sell you LDPC codes a little bit for practical purposes, so you can perform numerical simulations under quite realistic noise models. And yeah, if we take in this example, we take a two-dimensional hyperbolic manifold and let it run against the surface code or the toric code, which is like the currently favored coding scheme that's kind of pursued by IBM and Google and so on. And you see that yeah, we investing only a fraction of physical qubits, we can gain the same performance compared to the surface codes. Okay, so these were the geometric constructions. So let me switch over to the product construction, unless there's any questions.
I'm just curious about the whole volume thing. So, so I think you said something about how you would take a surface and you would evenly distribute the cells according to the volume.
Yes.
Is there kind of a reason on the practical side why we would do that?
So I think it's just more like a construction thing. So if we don't do this, so I mean there are constructions of codes where we do not do this. So we could, for example, we can take a hyperbolic. So let's say we take a Poincaré disk, and I could tessellate it by ideal triangles. So ones which have their vertices at infinity. Then I could still do this. I could still kind of define a tessellation, but then I would have like so I didn't talk too much about this, but then to obtain a finite code, first of all, I would kind of compactify this. So I would kind of find a finite surface which is tessellated in this way. But then the end result would not be LDPC anymore. So there would be automatically the check weight would grow with the size of the surface. So there's like maybe one reason why you wouldn't want to do, where you wouldn't want to pursue this.
I see. Okay, thanks.
Yeah. Any other questions? Okay, yeah, then let me introduce product constructions. And the idea is quite nice. So let's say we take two classical codes. I'm going to turn them into a quantum code. So I've already introduced CSS codes, and this was essentially the same thing, right? We had two classical codes, but in general, it's hard to find classical codes which are orthogonal, yeah. So which fulfill this this commutativity condition. However, in this product constructions, we can just take two arbitrary classical codes and turn them into a quantum code. And yeah, the idea is yeah, to kind of define this type of product. And the simplest example are just tensor products, or also called hypergraph products. And yeah, the quantum code will inherit its properties from the input codes. Okay, so let me switch again to the homology description of codes. So we will think of the classical codes, which I will call C and D, as these length 1 chain complexes. Yeah. So here is the space of bits of this code. Yeah. And here is the space of checks, and we have the parity-check matrix kind of mapping from one to the other, and similarly with the other classical codes. Then when we can define what's called a 2 complex, that I will call E, and this is simply given by taking the all pairs of chains and taking that normal tensor product, yeah. And there's a natural, immediately we obtain a natural maps between these tensor product spaces just by applying the boundary operators, yeah. So we can just apply the boundary operator of C, and we can map from C1 tensor D1 into C0 tensor D1. Yeah, and this way we obtain this this diagram, and then the idea is that we first of all we obtain a grading of these constituent spaces. So we just take the indices and sum them up. So here's like a 2-graded vector space. There are 2 1-graded vector spaces, and there's 1 0-graded vector space. And yeah, by kind of taking the gradings and then defining looking at then kind of, I know, taking direct sums of the equally graded vector spaces, we obtain what's called the total complex, which is called TOTE. And this turns out to be a length 2 chain complex. Yeah, and this is exactly the quantum code that we want to obtain. Yeah, so we obtain 2 matrices here. Yeah, again, because we assume that there's a distinguished basis on all of these constituents. So we also have a distinguished basis here, so we can kind of think of these as matrices. Yeah, so this is essentially like the homological view on this. But let's think about this more in topological terms. So for the benefit of those who might not be too comfortable with the homology description. And the idea is that we can assign a topological space to codes. So let's take a repetition code with 3 bits as an example. So which has code word 000 and 111. And this is its parity-check matrix. Then we can identify this with a circle graph by identifying the edges with bits and the vertices with checks. And such that the parity-check matrix is just the vertex edge incidence matrix of these. Yeah, so this is just the boundary operator of this graph. So now it's quite almost trivial. So we just take 2 of these repetition codes given by these circle graphs. We take their usual Cartesian product and we obtain a torus. And this is exactly the toric code that we've already seen a couple of times. Yeah, so this is a way to construct the toric code from 2 repetition codes. Yeah, so just to kind of, I know, relate this back to this diagram I showed before. So the faces are just the products of edges. Then there are 2 types of edges, which are products of the initial edges with a vertex or the other way around. These give us our horizontal and vertical edges in the torus. And then we have vertices, which are just products of vertices of the inputs. Okay. One intuition I want to kind of, I know, give you is about the distance scaling. So the size of the total quantum code is just the product of the input code length. Yeah. So if this is a repetition code on 3 bits, like or both of them, then we obtain a 3x3 tessellation of a torus. Yeah. Yeah, so this is like the scaling of the number of physical qubits in the product. There's something called a Kyneth theorem, which relates the homology of the input factors to the homology of the output. Yeah. So what this means in coding terms is that code words of the input codes of the classical codes lift to logical operators of the quantum code. Yeah. So in particular, if we take this 111 code word here, this lifts to an essential cycle around the torus. So this means that the distance in the product is just given by the minimum distance of the input codes. And these 2 facts that the number of physical qubits scales quadratically, essentially in the distance, just means that we have essentially an upper bound on what distance we can achieve. So the distance we can achieve are the ones which are essentially we cannot do better than square root n, essentially. And it turns out this is a bit of a barrier for a long time. Yeah, so this is the bond I just gave you. Friedman, Meyer, and Luo, they worked very, very hard using a very complicated 4-dimensional manifold to beat this square root by a 4th root of a log. Yeah, so by not very much. Then for a long time, there wasn't anything happening in terms of distances in quantum codes until Eva, Kaufman, and Seymour used so-called Ramanujan complexes to improve this by a square root of a log. And then Kaufman and Tesla showed essentially by taking iterated products of these Ramanujan complexes that you can get arbitrary polylog scaling. However,
can I ask a
yeah.
very basic question?
Sure.
Yeah, so could you go to the slide before?
Yeah.
Yeah, so is there a way to think of this in terms of like a real space picture, or do you have to use this? I guess you're saying this product of two classical codes, you had to do this mapping for vertices and edges. And so I guess, is there like a real space picture for like physical qubits for where you could get like a product of two repetition codes equals a toric code, or do you have to do this kind of abstract mapping first?
Yeah, so when you say real space picture, do you mean like more intuitive understanding, or
yeah, maybe. I mean,
okay.
like, I guess repetition code, I usually think of just like, you know, qubits on a line. And then...
Right. Yeah, so I think I have to disappoint you. I don't have any deeper thing I can tell you besides that. Maybe one thing I can say is, okay, for like classical codes, all that can happen are bit flips, right? So you only need to kind of correct like one type of error.
Right.
For quantum codes, it's essentially continuous, right? But then you have to do these like check measurements, and these discretize your errors. However, the errors themselves, they kind of decompose into poly X, poly Y, and poly Z and identity, because they span all complex matrices, all complex 2x2 matrices.
Right.
And Y is a product of X and Z. So essentially, there's only two types of errors. There's only X errors and Z errors that we need to correct for, and this is where these like two codes come from: the HX and the HZ.
Right.
Yeah, so we need essentially a space which is two-dimensional to correct quantum errors, and we need a space we only need a one-dimensional space to correct classical errors. So this is maybe I'm thinking in terms of these chain complexes. So we only need like a length 1 chain complex for classical, but we need a length 2 chain complex for quantum. Right. I think this is like the best I can do.
I guess that's kind of the picture I had in my mind. So I guess like, is this more general? Like, I guess if you have like a 2D classical code, you can make it into, like, if you tensor product them, you'd expect like a 4D quantum code or something.
Oh, okay, yeah. You can, yes. Very good. Yeah, so we can take, so chain complexes can be arbitrary length, right?
Yeah.
But we only kind of, I know, essentially we kind of cut out this length 2 thing in the middle usually. But you're right, there might be like, I don't know, more boundary operators kind of going here to the right or kind of coming from the left. And what this gives you is linear dependencies between your checks. And this can actually be advantageous, and I will talk about this a little bit later. So linear dependencies between the checks. So you have essentially like your classical information that you extract is also encoded in a way, encoded in a fault-tolerant sense. And this can be useful later. And I will kind of come back to that.
Okay, thanks.
Yeah. Okay, any other questions? Okay. All right, yeah, so then let me continue. Yeah, I was saying there was this issue with the distance scaling. However, there was a breakthrough by Hastings, Howe, and O'Donnell, who improved on this. And the idea is essentially to introduce twists. Yeah, so we don't have just like a normal Cartesian product, but we have some sort of twisted product. And again, to give you some intuition for why this works, let's look at the toric code again. So if we have a d by d torus, then the distance is d, because this is the length of the closest of the shortest loop. And we can, however, we can twist the torus, and this, in effect, increases the length of one of these loops. Yeah. So if we have, if this is the torus, yeah, with opposite sides identified, then in order to have like a closed loop kind of going around the torus, we have to kind of we have to loop up on itself. We have to do this this detour. Yeah. So this is the intuition. So why twists increase the length of these cycles. So the product that they do is between a random code, which I kind of just draw as this oval shape, and a repetition code, which again is just like this 1D line. If we were to do just the normal tensor product, then again we would have some check which comes from the checks of the input codes, And yeah, the code words of the random codes would kind of lift to a logical operator, and we would essentially have the same problem that we had before. So the repetition code essentially foliates this product space, and I use space very carefully here, since this is a random code, so there's no manifold associated to this. Yeah, but again, we have the same problem that we had before with the torus. So what Hessingshauer and O'Donnell did was they twist all the checks randomly. So instead of connecting within one layer, yeah, they introduce this twisting function, which connects far away layers. Yeah, they introduce this in the language of file bundles. I won't go into that notation, since we will see later this actually is dissolved in a different construction. But yeah, the distance scaling that they obtain is n to the 3/5 up to some polylogs. So this is much better than polylog n times square root of n scaling. And this was improved upon by Panteleev and Kalachev, who showed that, first of all, they gave a very clever new distance bound, and then they exploit this to obtain another randomized construction where they essentially obtain almost linear distance scaling. But again, these are randomized constructions, so these bounds hold with high probability only. And yeah, a different construction, which was introduced by myself and co-author, are so-called balanced product quantum codes, which are not randomized, but they require symmetrical input codes. So we take two symmetrical classical codes, which are symmetric under some group G, and we obtain a quantum code. And we use this construction to define two families of quantum codes. So first of one, which de-randomizes these earlier constructions. So one where we obtain number of encoded qubit scaling as n to the 4/5 and distance scaling as n to the 3/5. So we slightly improve on this result by Hessingshauer and O'Donnell. And we give another construction where we prove that this has linear encoding rate, and where we conjectured that the distance is also linear. So this would be the optimal parameter scaling that you can actually have. And this distance bound was proved by Panteleev and Kalachev recently. Okay, yeah.
Yeah, I'm going to ask a question. It's probably on the next slide, sorry.
Mm-hmm.
How does the group G influence the output parameters of the code, the N, the K, the D? I
will get to that in a second.
All right.
Yeah. Okay, let me first introduce balanced products. These essentially come from topology and representation theory, and the idea is that if we have two topological spaces, X and Y, with some group acting from the left and the right, then for every pair in the Cartesian product, we can define the so-called anti-diagonal action, and on the product. And then the balanced product is simply the quotient space where we take the Cartesian product and then factor out this group G. And yeah, by linearizing this notion, we obtain this balanced product construction. Yeah, in this more homological description. Okay, so yeah, just from the definition, it's not immediately clear what such a space looks like. So let me give you an example. So let's again look at repetition codes, which are these 1D cycle graphs. And let's take a distance 3 and distance 6 repetition codes. And these share an order 3 cyclic symmetry. Yeah, I can rotate both of them by 120 degrees. And yeah, by taking the Cartesian product and then factoring out this rotation, I obtain this twisted Tori code. Yeah. So again, opposite sides are identified here, and this is nothing but a topologically a torus, which also locally looks like the normal Tori code. But there's a skewing in the tessellation, and you can already see that this gives us slightly improved parameters. So we save 6 physical qubits by obtaining the same number of encoded qubits in the same distance. And yeah, so later it will be important that to kind of keep in mind the following geometric intuition. So by performing this variance product, I have taken the distance 6 code and kind of essentially kind of wrapped it around itself to form this torus. Yeah, just kind of keep this in mind because it will be important later. Okay, so now in order to define families, we require explicit constructions of symmetrical classical LDPC codes. And such a construction was given by Sipser and Spielmann in what's called expander codes. And these are codes where we take so-called expander graphs, which are sparse but well connected, and combine them with small block codes to obtain good LDPC classical codes. So ones where number of encoded bits scales linearly with n, and the distance scales linearly with n. And there's a very nice background to this, which I won't have the time to go into. But these expander graphs, especially the ones that we will consider, they come associated with the Riemann surface. Yeah, so we can always kind of think of these as two-dimensional, embedded on two-dimensional Riemann surfaces. Okay, but yeah, let me quickly kind of go through like the construction and give you the intuition of why this works. So let's take this Riemann surface called the Hilbert surface, which comes with this triangular tessellation. This has parallel boundaries and kind of looks like this. It's like this genus 3 surface. We identify the edges with bits and the vertices with checks. However, instead of just checking the total parity, yeah, so as we did for the Tori code, yeah, where we just look at the incidence relation between a vertex and all its edges, we check for code words of a 743 Hamming code, and these are all the code words which are symmetric under cyclic shifts. So now what I want to show you is what the code words of this large code look like. And yeah, in order to do so, let's construct a non-zero code word. So let's put a code word of the local code around the vertex. So let's take this one. So here I took 0, 0, 0. Then here 1, I make a thick line, 0, and then 1, 1. Yeah. So this is a code word, and all checks on this vertex will be satisfied. But now I created 3 problems. Yeah, since the distance of the local code is 3. And there's only one edge supported on here. These checks cannot be all be satisfied. So let me kind of fix this by adding putting another code word around this vertex. But again, you see I've kind of created more problems than I kind of finally solved, and I can continue doing this, and I create more problems. And you have to believe me that actually I can continue this, and actually I can solve this, and I can obtain a proper code word where all vertices, all local codes are satisfied. But I want to kind of show you or give you the intuition with this exercise is essentially the expansion of the graph. So the negative curvature, the fact that we explore more and more space by going radially outwards, plus the distance of the local code, they enforce that the code words will always have weight linearly in n. And proving this is actually not very hard, but I won't go into the details of this proof. Yeah. So yeah, I hope it's okay to kind of just give you this intuition and carry on. But before that, let me again kind of move back a little bit into homology. So this local code construction is a bit more general, and these are called tenor codes. And they have an interpretation in terms of homological algebra again in so-called steam-road homology. And this was observed by Mishulam in this paper. And the idea is that we have some function f which assigns abelian groups to the cells of our input space, and we also adjust the boundary operators accordingly. Again, so, apologies that I don't go into too many details. The point is that in our case, this actually simplifies significantly. As in our case, the function f for the edges is trivial. We just want to keep qubits there. And we assign checks, which I will denote by L0, to the vertices. And yeah, this assignment then just simplifies to the usual tensor product. Yeah, so instead of doing using this this Steamroller homology, you can essentially just tensor on these local codes. And what you obtain then is, again, this 2 complex. Let's say we take a product between between 2 input spaces, and we assign a local system to one of them. Then we can just kind of tensor it on. Okay, yeah. So apologies, this is a bit quick, but this is just to kind of show you this diagram essentially. Okay, so yeah, so the first construction that we do is we take an expander code, which is given by some parameter q. And maybe I can give you a bit more background. So these expander codes are Cayley graphs of the group PSL to Q. Yeah, so over the finite field FQ. And yeah, the size of this group is Q to the Q cubed. And we always know that there will be a cyclic symmetry of order Q in this group. Yeah, just by taking upper triangular matrices. Yeah, we have obtained this cyclic subgroup. And yeah, we can take a repetition code which has distance Q, which obviously has this Q-fold rotational symmetry. So this means we can define this balanced product. And what we obtain is essentially we take this Riemann surface, yeah, on which this Cayley graph of PSL2FQ lives, and we wrap it around itself, and then glue in these repetition codes. So this is essentially what we did what we saw earlier for the torus. Yeah, but now one of the inputs is this Riemann surface, so it's like a layered Riemann surface with these cycles glued in. So now going back to this earlier question, so what this group does. So the input spaces had the 2 volume here is Q cubed, and the 1 volume here is Q. So you would expect that the output space has volume Q to the 4, but we perform a symmetry reduction of order Q, and this kind of shaves off a factor of Q. Yeah. So this is why we obtain n being proportional to Q cubed here, rather than Q to the 4th. I should mention in this earlier work by Hastings O'Donnell and Matilda Kalachev, we had these fibers or lifts, and this is essentially these repetition codes that we kind of glued in. Okay, I already said that. Okay, so now the important part is again the code words of the input codes lived to logical operators. However, here the distance was linear, so it was the same as the size of the total space. And this again lifts to a logical operator, which again has a size given by Q cubed, yeah, which is linear in the total number of qubits. However, the repetition code here is what kind of limits us. So this only has size Q, yeah, because this is just an essential cycle kind of going in this direction. And yeah, but we can fix this by controlled tensor products with a different code, and this is how this is called distance balancing, and this is how we obtain these parameters. Okay, any questions so far? Okay, yeah. So then let me continue with the second construction. So here we take 2 good input codes, 2 expander codes, inputs, and instead of factoring out a subgroup, we factor out the full symmetry group. And now we obtain, so these are 2-dimensional spaces, and we take the product and then factor out this full symmetry group, and we obtain some horribly twisted 4-dimensional space. But the important part is that since the inputs are of order n, but then we perform an order n symmetry reduction, the output space is again only of order n. However, we prove a Quantities theorem for the balanced product as well. So we know that the code words of the inputs lift to logical operators of the same size in the output space. Okay, but there's a caveat. Of course, just kind of proving this Quantities theorem doesn't prove that they might not combine in like awkward ways. That there are actually logical operators of smaller size. But this led us to this conjecture that if we take the balance product of two good LDPC quantum codes, then we obtain a quantum code which also has these optimal parameters. Okay, and yeah, again, so we proved that the number of encoded qubits is linear using some homological algebra. However, this distance bound only works for abelian products. However, here the group is necessarily non-abelian, so yeah, we couldn't fully prove this conjecture. However, it was proved by Panteleev and Kalachev, who yeah, found like an ingenious new proof which applies to non-abelian products. And there's also like an additional nice thing that they showed where they rule out the existence of some low weight logicals. And they also prove a second open conjecture in classical coding theory. So these are so-called good locally testable LDPC codes. And the same conjecture using essentially the same construction was proved by Dino et al. And there's also been nice follow-up work by Levrier and Seymour and by Lin and Shea. So the latter in particular showed that like how to actually perform this the decoding operation. So the classical algorithm which takes the check measurements as inputs and computes the recovery operation. Okay, so yeah, I'm running out of time, so let me now kind of switch back to like the more overview part of why you would want to use LDPC quantum codes. So for that, I should say that currently the favorite scheme is the so-called surface code, which is just like a planar grid layout of qubits with local checks. And the reason that this is the favorite scheme is because the code itself is simple. The layout is planar, which is nice for certain hardware architectures, and has very good error correction capabilities. And therefore, it's the most mature fault tolerance architecture. So what LDPC codes could offer is, first of all, better parameter scaling. So now we know we can obtain codes with pretty much optimal parameter scaling. And yeah, this suggests that we could get less overhead in terms of physical qubits. And we could also obtain much simpler error correction procedures. And there's some no-go theorems which apply to the surface code, which shouldn't apply to LDPC codes. So one result which kind of kickstarted a lot of research in LDPC quantum codes is Grossman's theorem. Then Grossman showed that if we have a family of LDPC codes which have a constant encoding rate and an efficient decoding scheme with suitable properties, then it's possible to approximate a perfect quantum circuit using faulty components by using at most a constant overhead in physical qubits. And yeah, it was shown by Fasi, Grossman, and Levrier that the conditions of Grossman's theorem can be fulfilled. And they take this normal tensor or hypergraph product of classical codes, and they introduce a very simple flip decoder, which works a little bit like this cellular automaton I show you here. So it just kind of looks in local neighborhoods and then performs flips. And yeah, so this is fulfills Grossman's conditions. Yeah, so I already said simplified decoding. So there, besides the simple flip decoders, there's also a so-called leaf propagation decoder, which is widely used in classical coding theory. This is a very simple message passing algorithm. And yeah, these flip decoders they use once we have a notion of expansion. Yeah, so this kind of suggests that we need something which is non-Euclidean. Okay, we already had this earlier question about these like longer chain complexes, and this property that our our measurement results are themselves encoded. This can be helpful for so-called single-shot decoding, where we assume that the check measurements have to be subject to noise. And so this is detrimental for the surface code, as we have to repeat our measurements to kind of gain some confidence. However, single shot means that no repetition is needed. And LDPC codes can exhibit the single shot property either through this linear dependence or through like some other means. But what I want to say is that LDPC codes can be inherently robust against these types of noise. Okay, I'm really running out of time here, so let me just kind of really quickly gloss over this. So one challenge are logical operations, so how to manipulate the information encoded. There has been quite recent work kind of in this direction by Krishna and Pula, by Cohen et al., myself and Simon Burton, and also by Quantities and others of implementing logical operations. Yeah, but it's in the very early stages. Okay, so let me gloss over this a little bit. It's important. So I want to say, okay, there's like a notion of dualities, which makes it possible to get a handle on what fault tolerance gates can be present in LDPC codes. Okay, so let me kind of finish with the big challenge, which is probably on all of your minds, namely how we would kind of possibly build these things in physical hardware. This can actually be quantified by a result due to Breuckmann and Krishna. So if we have an LDPC code with high distance, then we need lots of connections of increasing length. There are some solutions to this. So first of all, we could just kind of, say, okay, we only care about architectures which are not bound by planarity, and there are actually quite a few. So there are photonic architectures. Then even architectures which are usually planar, so for example, transmons. IBM, for example, they are now looking into modular architectures where they interconnect fridges, and then this kind of frees us up from any locality constraints. Or quite excitingly, there's work on qubits which all live in a common cavity, and they are coupled by a common cavity mode. Also, we might not be might look into codes which have a little bit of non-planarity. So we could embed codes on a small number of sheets in a planar way, and then kind of interconnect the sheets at a common interface. And this would already kind of give us enough wiggle room to obtain interesting LDPC codes. Okay, so let me summarize. I hope I gave you a glimpse into quantum LDPC codes and showed you why I believe that they are promising alternatives to the surface code. There's still more work needed to make them attractive. There's still lots of questions. Yeah, again, so this was only a very brief overview. So if you're interested, please look into our review article. Thank you very much.
Great, thank you. So I will go ahead and stop the recording, and then we can do the Q&A.